All right, so we are going to be starting our first topic here is kinetics. Um, does anybody know what kinetics is all about? All right, that's why we're here. So in kinetics, what we're ultimately interested in are reaction rates, how fast or how slow a reaction is going. And we're using this as kind of a start point because reaction rates themselves are something that we can get a pretty easy handle on, and it kind of fits kind of closely with some of the stuff that we saw in Chem 105. A lot of the reactions that we saw in Chem 105 were one directional, where we had reactants and we had products, and there wasn't a whole lot of reversibility. And we also saw that some reactions were fast and some reactions were slow. You put um, an acid and a base together, they react pretty quickly. But you also saw other kinds of reactions that developed a lot more slowly. Take, for example, the copper sulfide reaction that you did for the empirical formula lab. That reaction took good 15 minutes to form, and then an additional 5 to 10 minutes to burn off all the extra sulfur. So we can understand that there are different kinds of reactions, and some of them go fast and some of them go slow. And so our main focus today is going to be over these topics here, where we're going to talk about what kinetics is. We're going to introduce a theory that kind of helps us to explain kinetics and what might make a reaction go fast or slow. And then we'll talk about some of the ways that we measure reaction speed. Tomorrow, we'll talk about primarily focusing on concentration and how we can monitor a reaction speed based upon concentration of the reactants. And then on Monday, we'll close up the unit by talking about some different experiments and some what are called reaction mechanisms, where we try to theorize how a reaction actually takes place to give us our rate laws and to help us make sense of them. So I want to pose this question to you here at the start, and it's this. Since we are talking about reaction speed, let's brainstorm some ideas. What are some factors that we can identify that might help us to determine how quickly or slowly a reaction might go? So I know there's only 5 of you in here, but get together, come up with some ideas, talk some things through here. So we're hitting on some good ideas here. And in some way or another, each of the things that you brought up probably are in some way correct. So getting into the material itself here, kinetics is what ultimately helps us to study this idea of speeds of reaction, rates of reaction. And there are a number of factors that are included in this. I heard you mention temperature and pressure. Both are certainly going to be impacted and have an impact on that. Concentration definitely has an impact as well. That's what we're going to focus most of our study on tomorrow. Catalysts. What is a catalyst? Anybody know? Okay, yeah, you're pretty close. So yes, a catalyst impacts the reaction speed without changing the makeup of any of the products. the catalyst itself is also not impacted in some kind of way. It starts out and comes back in the same form that it was initially. So it's not consumed in the process either. And then things like mechanical force. I heard someone mention stirring. That's that kind of agitation. Mechanical force can also mean like changing other kinds of conditions. But agitation, stirring is probably the most common. So how do we contextualize this? How can we kind of put a nice formal way of trying to explain why one reaction might go faster than another? Now, for that, we're going to need kind of a unifying theory for how chemical reactions work. And that unifying theory is called the collision theory. The collision theory is really simple. And if you kind of put it on its face, it makes a lot of sense. In order for a chemical reaction to take place, the reactants are going to have to encounter each other. They're going to have to collide. And so, yeah, on its face, this makes a ton of sense. I can't have reactant A and reactant B turning into something else if they're not even going to touch each other in the first place. We can't send electrons telepathically from one species to another to make new bonds. They have to be close enough to interact. So it only makes sense that they would also collide in that kind of situation. But the other half of this theory is really where things kind of come together. I think if I gave you the question and asked you to think about it long enough, you would probably come up with the idea that the reactants have to interact with each other, that they have to collide. But the last two parts of this theory might not have come together for you nearly as quickly. There's an energy and an orientation component to it as well. So in order for the reaction to take place, you have to have enough energy present that the reactants are going to break their existing bonds to help form new ones. It's for this reason some reactions never take place at a given temperature. And this doesn't apply just to chemical reactions, this applies to physical changes as well. You can try as hard as you like, but if you have water in a freezer at negative 50 degrees Celsius, you're not going to see it boil. There's a temperature component to it. The molecules don't have enough energy to break out and go to the gas phase. You can combine copper and sulfur in a crucible, and you can mix it as hard as you want. But if we're only at room temperature, it's going to just stay a mixture of copper and sulfur. There has to be an energy input to force those bonds to interact, to force those atoms to come together. So energy has to play a part in it as well. The other part is the spatial orientation part. Now, in atomic reactions like the formation of copper 1 sulfide, that's not usually as big of a deal because they're atomic samples. So really, the energy is the only thing that we have to overcome. But if I'm dealing with molecular kinds of substances, there's a big difference. Let's just put this in terms of the reaction that they gave us. I have reaction, if I have A here, and BC looks like this, there is going to be a difference between A bumping into B versus A bumping into C. If the A bumps into the B, I'm not going to get the products that I want here. Because the product here is A bonded to C and B by itself. Well, if A bumps into B, the energy of that collision is going into A and B together. The only thing that could happen, is going to happen, is that A and B bond and C gets left behind. But that's not the chemical reaction. But if A bumps into C and forms bonds with C so that it can kick B out, then we have the reaction that we are interested in. And so there are only a couple of orientations where that would actually work and make sense. If A bumps into B, nothing's going to happen. If A bumps into the middle of it, nothing's going to happen. But if A bumps into C with the correct energy, yeah, possible reaction can occur. And so this is what the collision theory ultimately is getting after. In order for something to react, we have to have molecules colliding. Those molecules have to collide with sufficient energy and with the proper orientation. If those three conditions aren't all met, the reaction is not going to take place. And so when we start to examine the concept of what might make a reaction go faster or slower, we need to keep this idea in mind as we're going through it. And so here's a less theoretical example. Here we have nitrogen monoxide reacting with ozone. The products of that reaction are nitrogen dioxide and oxygen. And what we can see here is that we need the oxygen of the ozone to knock into the nitrogen in the nitrogen monoxide so that it can create the nitrogen dioxide. And so we see in the first example, we're not going to get an effective collision there because it's knocking into the wrong oxygen. If it knocks into that center oxygen, you can't form bonds there because the oxygen in the middle is bonded to the other oxygens on the sides. You can't pluck the middle out of a molecule and expect the resulting other atoms to just magically come back together. You can't have the oxygens collide for the same reason. But if you have them come together at the right orientation with the proper energy, the result is going to be that we get a chemical reaction taking place. Bonds are being broken between the oxygens and ozone and formed between the oxygen and the nitrogen in nitrogen dioxide to give you our product. Now, one other thing that comes into play with collision theory is the idea of activation energy. Now, by definition, activation energy, which is given to us as EA, E sub A, this is the minimum energy that would be required for a chemical reaction to get started. And we're never going to see a chemical reaction take place unless we get over this energy barrier. And so this is really kind of what's happening when we look at reactions like combustion reactions. We know that propane and oxygen will react to make carbon dioxide and water. We know that will happen. But if we are at room temperature, sufficient energy is not existing just here to overcome the activation energy of that reaction. We have to introduce some kind of energy to get the whole thing started. What do we use for that energy? Matches, lighters, flint and steel, laboratory strikers, ferro sticks, whatever we have access to. Electronic impulses. That's what overcomes the activation energy. Similar kinds of things. So, why does your car have a spark plug? If you have a gas engine, the spark, that's your activation energy to burn the gas. Without it, even if with high pressure, it's not enough energy to get that gas mixture to ignite. Spark comes in, generates that bit of activation energy, burns the fuel to push down the pistons to keep the engine running. Now, if you're talking about a diesel engine, slightly different mechanics there. But the idea is still the same. There is a certain amount of energy that is necessary to overcome. It exists in all chemical reactions. The main difference between some reactions and others, how big is that energy hill that you have to climb? If it's relatively small, like in a combustion reaction, it requires very little energy to get it going. If it's incredibly large, it gets into that territory where it's either very hard to sustain or it's not going to be spontaneous in that particular direction. We usually look at it in terms of the opposite direction, because chances are pretty good that if it has a high activation energy and it's endothermic, then the reverse reaction is usually much easier to do. So one way that we can show activation energy and put it in context of some other concepts that we've seen, these are called reaction coordinate diagrams. These are energy diagrams. And so we can see that in these graphs, we have energy in the y-axis, and we have the reaction progress on the x-axis here. Now, if this looks familiar to you, think back to the thermochemistry unit from Chem 105. We did just a tiny bit of this, where we were looking at endothermic versus exothermic in terms of where reactant energy versus product energy was. The only thing that we were really missing in those diagrams, we had no concept of activation energy yet. But we talked about exothermic reactions as being those where the reactants had less energy than the products, because in the process of the reaction, energy is being released. And if you remember to the discussions of system and surroundings that we had in thermochemistry, with the reaction system being the system and everything around it being the surroundings, including us, exothermic reactions feel hot, or at least warm to us. And the reason they feel that way is because the excess energy that is being released gets released to us, and we feel that as warmth. But on the other hand, If the reactants are at a lower energy than the products, that means that we had to absorb energy to get the reaction to proceed. That is an endothermic process. Endothermic processes to us feel cold because as the system is pulling energy in from the surroundings, that means it would be pulling in energy from you. A loss of heat energy on your part would feel cold. Now, adding in the piece here, what we can see is that activation energy is this energy that exists to get us over that mountain to allow us to turn the reactants into products. And it does not matter if it is an endothermic or an exothermic reaction, that activation energy will always exist. Now, when we talk about mechanisms, we'll get into better discussions about what that transition state is and what intermediates are. So don't worry too much about that at this point. We will come back to it though. Basically, to give you the 5-cent version, transition states are the highest energy mismatch of the reactants coming together. So if you can imagine what that thing would look like when they collide, right as the bonds are kind of transferring, that's what the transition state is. It's super high energy, it's very unstable, and that's why after the transition state, we always see a release of energy. Doesn't matter if it's exothermic or endothermic. The transition state is a higher energy form of the kind of reactants and products coming together before the final products are generated. Now, one of the things that can play into our ideas of reaction speed, we can talk about phases of matter. So when we have homogeneous reactions, where all of the reactants are all in the same phase, these reactions tend to be faster. And the reason they tend to be faster is because since they are all in the same phase, they are all interspersed with each other, they're all commingling with each other, and the likelihood of getting effective collisions is a lot higher because of those factors. When we deal with heterogeneous reactions, though, where we have reactions in different phases, then it becomes a matter of surface. Because if we have a gas intermingling with a liquid, the only place where the gas and the liquid can interrelate with each other is at the surface of the liquid. And so we're going to have a lot more difficulty getting effective collisions because, well, there's only a certain limited area where they can actually interact. And we see this especially with solid phase. Solid phase reactions tend to have a lot of difficulty. And that's because it's entirely related to surface area. The greater the surface area, the more interactions are going to be possible, the faster the reaction is going to go. And so when we are dealing with heterogeneous reactions, surface area is going to be probably the biggest factor that we look at, even more so than temperature and pressure and those other things. Because if I have a high concentration, but it's all wadded up into a rock, it's going to be a lot harder for that rock to interact with the things around it than if I took that rock and smashed it into a powder. So let's look at some other examples of kind of some of these concepts in action. So the effect of concentration. So here in the pictures, we have two different examples of steel wool burning. In the first example, up here on the top, we have steel wool that is just being burned in a normal Bunsen burner flame. And we can see that, for the most part, it is burning. We can see that the wool is glowing. And if we pull the wool out, we see that it has transformed. There is a black oxide coating on the steel itself. But the reaction itself is kind of slow. We'll see a couple of whispers of wool just kind of breaking off. But if we change the environment, we go from burning the steel wool in open air, which is about 20% oxygen, to isolating oxygen almost purely here in this flask, to where it's close to 100%, we see that the reaction becomes much more vigorous, much more energetic. And the only thing that changed is the higher concentration of oxygen. So when we deal with higher quantities, higher concentrations of reactants, the reaction speed is going to increase. Now, like I said, tomorrow we'll spend most of our time quantifying that relationship and trying to put it into contexts of the chemical reaction itself. But for today, we'll just focus on the idea of it's going to go faster this way. We also know that as we increase temperature, reaction rates are going to increase as well. This has more to do with kinetic energy than anything else. We know that as we raise the temperature, the internal kinetic energy is also going to increase. And so if our internal kinetic energy is going to increase, two things are going to happen. First, by the fact that they are moving around more, we are going to have more collisions in general. Now, I don't know how many of you are into probability and statistics or just like them in general, but the general concept here, more collisions means that we are going to at least have a better chance of getting effective collisions at the same time. Now, it doesn't hurt that these molecules are interacting with each other at a higher energy, and so the chances of overcoming activation energy are higher as well. So increasing the temperature does two things. It's not going to help with the spatial orientation part, but by virtue of the molecules moving around faster, we know that they are going to interact and collide more. And by the virtue of the fact that they have more energy, we know that more of those collisions are going to have proper energy. We've covered two of the three conditions. By sheer probability of numbers, we would assume that would mean that we would get more effective collisions just because we would have, since we are having more collisions, period, more of those collisions would also have the proper orientation.